Okay, everyone, hello. Again, a quick reminder, if you've found anything lost property-wise, pass it to Reggio. If you've lost anything, in particular, for the women in the room, there was something found in the women's toilets, please check out Reggio, they've probably got it for you. Okay, the next talk is by Dan Reif, and Dan is a production engineer on the MySQL infrastructure team at Facebook, which has automated the management of tens of thousands of MySQL servers in the largest deployment in the world, almost exclusively with Python. Please thank Dan for his talk.
So I thought that that particular custom is weird but wonderful, right? Because now we're setting a really high expectation. If I don't earn that applause, you can take it back at the end, okay? So to talk about Python packaging at Facebook, it's first important to talk about what Python is at Facebook. And the answer is that it is the primary language for production engineers. The entire Facebook contingent that's here is production engineers, which leads to a pretty obvious question. The hell's a production engineer? Sorry, I was told I'm not supposed to curse. The heck is a production engineer? And the answer is a production engineer is a jack of all trades, right? So we have a little bit of coding, we have a little bit of network, we have a little bit of security, we have a little bit of this, a little bit of that, a little bit of everything else. It is the T-shaped expertise, right? So we go very, very wide, but then there's one or two areas where we go very, very deep as well. So Python is the cure-all. Put another way, it is the glue that holds Facebook together. It is hundreds of thousands of lines of code supported by many more hundreds of thousands of lines of code. So we build our actual core services in Python, but then we build the support structures for those largely in C++. So things like thrift, for example, are in C++ and expose bindings up into Python. All right, so I've convinced you that we actually use Python at Facebook. The question then becomes, why do we need to package it? Well, this is the biggest reason why, right? We have thousands of engineers. We have a number of interns that isn't zero. And all of those engineers and all of those interns are constantly making changes. So it's important that our packaging format, if it ever worked, right, if the program that you just packaged ever worked, it keeps working. And to pin all those dependencies, because all of those engineers and all of those interns, cough, cough, subscribe to this model, right? And that's wonderful, and that's great, and I'm really glad that they do, because it produces wonderful results. We can move fast, but it also means that when they change some of those dependencies, we can't be the ones that fall over. Our package has to be reliable. So, works once, pin dependencies, and so on. The other reason is to ease distribution, right? So if you have a new version that you'd like to push out, it's really much more handy to be able to push out one file than 2,000. Now also imagine that you're testing a new version. So even if you have a very advanced way of pushing things out that's, all segmented by version numbers, and maybe it has a symlink structure or something else to help you, if you aren't pushing forward the version number, that doesn't help you at all, right? So when you're testing new versions, it's handy to be able to package things up in one package, because then it can all go out in one slide. So I therefore have for us a modest proposal. Anyone who's snickering right now is an arts major. So a modest proposal, like the original modest proposal, is not at all modest. It is something that can't actually be done. But it's what we're going to aim for. So we're going to aim for something that's fast. Why does it have to be fast? It has to be fast because we're launching this hundreds of thousands of times, right? When you think of the fact that Facebook has hundreds of thousands of servers, even if a given program is only run once on each of those servers in its entire life, it's already been run hundreds of thousands of times. That means speeding it up has a real benefit. It also needs to be easy to use. That's because you remember all those engineers and interns I talked about earlier? The reason we hire them is because they are delightfully lazy, just the way we like our programmers, right? And because of that, if we make it hard to do this packaging, they're not going to do it. They're going to go out and do it their own way. They're going to deploy giant blobs into site packages or whatever it feels like. At the easiest way for them to do. For the person running it, they have an even lower threshold. It has to be indistinguishable from just running a normal binary for them to run this packaged binary. Okay? It also has to be flexible. And that's because we don't know what's coming down the line. When we first started developing pars, which is what I'm about to talk about, I didn't mean to use that word yet. When we first started developing pars, we were on Python 2. These days we're on Python 3. We had to be able to make that transition. When we first started developing pars, we didn't realize that people were going to want to also use that same format to package up Lua, but they do. So all of those things feed into us being flexible. And lastly, it needs to be independent, right? So it needs to be entirely separate from the system as far as we can make it. Because after all, that's how we get our concept of being free of dependencies. Okay, so what is a par? A par is a Python archive. Now I'm allowed to use the word. It's a zip file. Anyone not know what a zip file is? Okay, good. So it's also a shell script. It's also a Python program. It's actually all of these things, right? And they're all baked together into one. So let's take a look at par version 1. This was from the dark ages. In fact, it's so old I literally don't know when we started using it at Facebook. I tried looking and it crossed one of our transitions between version control systems. So long, long ago, in the dark ages, back before a disturbing number of you were born, par version 1, simple self-extracting zip file, and couldn't be simpler. What does it do? It extracts to /temp/something, and then it calls main.py. Okay? So you can imagine exactly how that would work, and we called this zip, because that was the only thing we had at the time. We also called it par, but we're going to name some of these with nicknames so I can refer back to them. You don't have to remember version 1, version 2, version 3. So this is a zip par. So what does it look like? Well, it kind of looks like this. I hope you have really good eyes in the back. So I'm going to break this down. This is the whole thing, right? All this. This is just the top piece. So the very top, like any self-respecting script that you can run, has a shebang. It then contains, remember how I talked about flexibility? Turns out people want to run these things on Macs. Great, why not? So it contains a little Mac compatibility. Then it contains a super secret function that I will never tell you the details of until 3 slides from now. Finish of that function. We then grab the build UUID. This is a randomly generated, it's a UUID 4. It's a randomly generated UUID. That's necessary because even if we are at the same exact moment in the HG source tree that we're building from, it's possible that we haven't committed our changes yet, thus we're actually at a different version. So we simply randomly generate a new UUID every time, and that's where we unpack to. So it's /temp/blah, right? Okay. We then set a couple of the linker variables, good, clean, fun. We unzip our contents into the tempter that we've selected based on our UUID. We then muck around with Python path and Python home because we enjoy pain. And then we exec into what we just unpacked. Easy enough, right? Everything below that is the zip file. Because zip files have the very handy little trick of when you open a zip file, ignoring everything up until it finds the magic zip file signature, which starts with PK. So we can put whatever we want at the front, and it is a zip file, just a zip file that happens to be also a shell script at the beginning. Now, everyone at Facebook loves iterating on things. So what do? We say, hey, we can do better. So we take that same self-extracting zip file, but now, instead of extracting everything, we use a handy little piece of software called zip import that allows us to keep all of the Python files inside the par. We only have to extract the non-Python files. Now remember I said that we are supported by a whole bunch of thousands of lines of code of C++. Those all end up compiling down into a variety of .sos, libraries, right? So those we have to extract. Zip import for all of its amazingness, is not able to overwhelm the capability of the linker to load shared objects. But otherwise, we can leave all the actual Python in the par. So that saves us from having to write it to temp. This is great, right? Because that means that we have now, we've now reduced the amount of disk churn that we have on every single par run. Except, sorry, we'll call this fast zip, except, oh, damn it, I screwed up that transition. This is what this looks like. All right, so the par file is stuck onto sys.path, and then the os.curter, which is that tempter, right, that tempter with the UUID, only contains the .sos. So this is great, except, there we go, that everything's broken. Okay, so when everything's broken at Facebook, it's not as subtle as when everything's broken some other places. I don't know what social network this is a screenshot from. It doesn't look very important, but wherever it is, emphasizes the fact that when Facebook goes down, people literally call 911, 000 in Australia, right? And so the LAPD had to, a word starting with T, that people should stop calling them to report Facebook being down. So failures have a big impact on the world. Who knows what this does? Anyone recognize it? Someone just yell out, what sort of cron job is it? How often does it run? Every minute, okay. So I said we had hundreds of thousands of servers. Let's just pretend for a minute that we have only 100,000 servers and that we have a bug that happens if something happens at the exact wrong millisecond during launch. I mean, what's the odds of that, right? The answer is that with 100,000 servers, we're launching 1,667 times a second, or 1.6 times per millisecond. So that means that what you might know is edge cases, right? So if you have an algorithm that takes from 1 to 10, and edge case is 1 and an edge case is 10. And what you might know is corner cases. So you have two algorithms that touch each other, and you give one of them 1 and the other one 1, and oh, look at that corner, it breaks. Those hit so often that the site is down immediately if you put out something with an edge case or a corner case. In fact, what you have to worry about are the vertex cases, because the vertex cases just wait a few minutes and then take the site down. So let's look at what we ran into. We have TempWatch. TempWatch goes through the temp directory and deletes old files. Thank you. Very nice of it. We have upgrades. What do upgrades do? Well, upgrades replace the par. There used to be a par named something.par, and now there's a new par named something.par. And the worst possible timing. So what happens? The worst possible timing happens. And we launch a par, and as it's in the middle of launching, we replace it underneath and run TempWatch. And all of a sudden, we are referencing a .py file that got refactored into another py file, but that other py file exists only in the old version, not the new version, and everything breaks horribly. Okay, great. So what do we do? You remember how I told you I'd never tell you the secret? Here's the secret. That little function is readLink-E, which is just a version of readLink2 that goes all the way down to metal. Like it just goes until it can't go anymore, right? And that allows us to open the par as an FD during startup. So what that means is, inside of Linux, a file isn't deleted until all references to it are deleted, right? You have the nlink count. This increases the nlink count. Therefore, we get to keep our file around even after it's deleted or replaced. This is RM-proof FastZip. So it looks, I mean, I don't know, I'm sure all of you have eidetic memories, but right here, this simply used to be the par file. Now it's /dev/fd/whatever. But functionally, it's the exact same thing, right? So the only real downside of this is that now you're tracebacks look crazy. Your tracebacks are /dev/fd/whatever/numpy/numpy.py. And it's not like you can go vim that, because that file doesn't exist, right? But otherwise, it's great. Okay, so remember how we keep iterating on things? Well enough wasn't good enough. So now what we do is we take all those files that we extract, all those .sos, and sometimes they're like little .texts or license files or whatever else, and we put them into a content addressable store. A content addressable store, or CAS, is one of those $5 words that basically boils down to this. You take a checksum or a hash of the content, and then you store it under that instead of under the original file name. So if you have 2,000 different files named 2,000 different names, but all of them have the exact same content that says, hi mom, my name is Dan, you only store one copy of that, and all the others simply point in. So that allows us to then hard link each of the files that is being extracted back into the CAS. So by doing the hard link, that means even if TempWatch comes in behind us and deletes a file from a unpack directory that we haven't touched in a little while, that's fine. Even if it deletes, in fact, the one from the CAS, that's fine, because we still have hard links to it. We're incrementing that end link counter, thus it never goes away. So we call this fastzip CAS. So what does that look like? Well, let's start with rmproof fastzip. You remember that one? Now watch closely. This is going to shift a little bit on you. Whee! All right. So at runtime, t1.par still has the exact same thing, right? So devfdx still goes back to that par file just like it did before. But we now have a different tool, tool T2, running at the same time. And that tool has the same lib1. Well, now at runtime, they actually share the same lib1 file. Okay? And then tool1.par has version A of lib2. Tool2.par has version B of lib2. It doesn't matter that they're actually the same library, because we're hashing on the content, they're safe, right? They point to their correct version. Okay, so fastzip cas. Now, well enough isn't good enough, so what do? We now say, wait a minute, we've got all these Python files that are just shared, and all these .sos that are built once and then just shared across a whole bunch of different pars that are getting distributed together. So you might imagine if core utils were written with pars, which thank God they aren't, but if they were, you'd have RM and MV and all these other, and cat, right? All these tools that were all built at the exact same time, pushed at the exact same time, they were put into a package together, and all of them had to have their own copy of every single library. It's just silly, right? So why not share some libraries between them? So the way we do that is we add a second zip. That second zip also added to systop path, just like all the others, right? It only contains the non-conflicting files. So if you have a version A of a file and a version B of a file, then each par gets their own individual copy of version A and version B, depending on which one it needs. But if they all have version A, then we can put version A in the S par, right? So this additional sparse par. The biggest trade-off is that it means that building a par is no longer something that you can do in a vacuum. You now have to understand which pars go together, and your distribution now has to also be done in that same way. You have to be able to distribute pars together, because if you can't distribute the S par along with the par is useless. Okay, so we call this sparse. And this one also, I have a nice little slide here, right? So in this one, these are at rest. Remember before we were looking at things at runtime. So this is at rest. We take this duplicated PyC and this duplicated .so out of each of tool 1 and tool 2, and we move it into the SPAR. Okay? So with two tools, and let's say that this represents half of the size of each of these. With two tools, we've gone from 1, 2, 3, 4 copies to 1, 2, 3 at rest. So we've saved ourselves a quarter of our app weight. But if we had, instead of 2 tools, we had 50 tools, all of a sudden we've shaved the vast majority of our app weight off. It's worth comparing this, though, going back a minute, to the fast zip cast. Fast zip cast does something kind of similar, but it does it at runtime, right? So we get kind of the advantages of both worlds here, because with Sparse, we're doing that at rest. We're getting all those benefits in terms of transferring things over the network, writing them to disk, everything else. Whereas with Sparse, we're getting, that's with Sparse, we're getting all this benefit. With fast zip cast, we're getting them at runtime. We're avoiding having to extract things that already matched. Okay, so this is about when I showed up, by the way, is that I took a look at this and said, wait a minute. What we're doing is we're extracting all these libraries, but these libraries often look a little bit like this. So this is fast zip cast. What was actually happening, the reason we had a version 2A and a version A and a version B of lib2 is that version A had, let's say, some functions that gave us addition and subtraction. Version B had addition, subtraction, and division. We don't actually need version A, right? Because everything that tool1.par needs to do, when he calls into this library and he says, hey, teach me how to add something together, the other version could have given them that answer. Likewise, teach me how to subtract something. The other version could have given them that answer. So we simply do this, right? We no longer store version 2A at all. We simply store version 2B. So for each.so, check its list of exported symbols and construct a polytree, saving only the roots of each of those trees. Polytree being, of course, a directed acyclic graph that has one or more roots. Okay, I like pictures. This is a polytree. So never mind all those CSE words. I totally dropped out of CS. It's okay, you can too. Don't tell your mother I said that. This is what it is that we need to only keep A, B, and H to be able to descend to any point in that graph, right? We can't not keep H because we then can't actually arrive at H by going only down arrows. We'd go A, D, G, I, but we can't get back up to H. So if each of these are superset-subset relationships, that means that A is a superset of everything below it except H. B is a superset of everything below it except A, C, and H, etc. So we can just keep A, B, and H. The downside is we can't share the libraries, even libraries that have the exact same set of exported symbols, so the exact same set of functions that they implement, between different SPARs that were built at different times. And why is that? Anyone? Exactly, yes. So imagine we had a function that was named give me the best number ever, and it currently returns 2, and next week it returns 3. The name of that function is the exported symbol, so that doesn't change. But the implementation underneath did. So we need to be able to pin that. Remember, these need to stay independent. These need to not be able to be broken by some intern doing something silly. So that means that super sparse, which is the name of this, the SPAR computation can't be shared between different SPARs. All right. Then, remember the flexibility thing? PAR 2.4.1 is very simply that PEP 3147 broke things for us. And it broke things for us because the zip import module doesn't understand the new PyCache directory, which is a great thing that should totally have happened, except that it broke zip import for us. So we simply repack it because Python 3 still knows how to read the old Python 2 locations of .pycs. Instead of them being under PyCache, they're alongside the PYs. So as part of building a PAR, we simply move it. No problem, right? But this feeds into the flexibility argument of how we design a packaging system. And then there's Python version 2.5. This one is from about last week. I technically pushed it just before flying here. So For standalone pars, that is pars that are not part of an spar, we would unzip them into the content addressable store, but in order to do that, we would hash their contents to figure out where they went in the CAS. It turns out that running a whole bunch of SHA sums on a whole bunch of data that you know isn't going to change after you generated it is kind of silly. So we were able to decrease launch time by about 25% by stopping doing that. So this is called Prehash. And then there is the version from outer space. This is from the future. So Czar is a complete rethink of the way that pars work. So instead of it being an executable shell script with a zip file, instead, it is an executable shell script that then mounts itself as a squash FS with an offset. What's great about that is that it means we can get rid of zip import. Zip import is kind of old and crusty at this point. Like I said, it doesn't understand PEP 3147, amongst other downsides. Also, one of the consistent problems that we have is third-party source going, I need to read myself. No problem, I'll just grab my own entry out of sys.path and start walking up and down the tree until I get to my file. That totally doesn't work if you are sitting inside some proc FD whatever, right? But it would work here. The downside is Fuse ain't free, so this is implemented with Fuse. And there's no built-in sparse option, right? It becomes much harder because sys.path doesn't work that way. So again, this is called Czar. So great news. This is what it looks like when your package has arrived. But overall, the message that I want to give is that at a lot of these talks, I often hear from the very, very biggest players, and they're like, so we were sitting around a conference room, and we called up scientists at NASA and the world's best, X, Y, and Z, and then we got in our academic partners, and together we were able to create the ideal X. And here's what it is as spake by God himself, right? That's not how development works. And I think we all know that. And every time we go into a room and we give those people credence, we lose our own sense of ourselves as developers. My hope is when you looked at this, you saw some of the things that, hey, wait a minute, I could push that 1%, right? Or you saw, what if, you started thinking of timing attacks against this, right? You're like, hold on, I can come up with a vertex case for this. That's the sort of thing that real developers do, and that's what gets me really excited, and that's what we're doing here. So if that sort of thing appeals to you, come talk to me afterwards, get a card, talk to us about Facebook. Even if you don't come to Facebook, you're the kind of people who I want to be talking with. So thank you so much for showing up to my talk. That's all I got.
Thank you, Dan. We've got a couple of minutes for questions, so does anyone want to get us started? Okay.
Only pick the ones who look like they have easy questions, please.
That looks pretty cool. Also looks like it was a lot of effort over a long period of time. Were you resourced specifically, or people resourced specifically to do that, or was it just something that people took on for themselves?
That's a great question. I am delighted to report that this was not at all in my job description, to put it mildly. And yet, I just basically woke up one day and decided I was going to do it. The way that things at Facebook work is that the only person at Facebook who can't tell you what to do is your manager. Everyone else says, hey, I'm having this problem. And then you have to come up with a solution for them. So when my team members were saying, hey, we're having problems pushing out our package because our package is getting too large, right? And literally we push out one of our packages via rsync and the whole 9 yards, right? BitTorrent, that sort of thing. There's an upper limit on the size of the package that we can push out that way, and we were bumping up against it. So we kept deleting tools from our package, and we made this bigger and bigger omnibus tool that contained all of our other tools. And I said, that's silly. Tell you what, I'm going to take a couple weeks and just do this. A couple weeks turned into a month. That's unimportant. But what ended up happening was super sparse, and then from there it kept iterating. So all of the Mac support, for example, that was just someone who wanted to run pars on their Mac. So they're like, I'm blocked by this. Here's a patch. I'm like, seems reasonable, approve. And it went in.
Cool.
Okay, any other questions over there?
So you've got a couple of 100,000 Python files there. If you're all using field descriptors and UUIDs to package them, how do you know which one has broken?
So I think there might be. I actually leave the mic with her there for a second because I might need clarification. So we use those UUIDs to identify the package, not the file within the package. So the UUID is a tuple in a sense of the package being built, like the name of the tool, comma, who built it, comma, where they built it, comma, when they built it.
Okay.
So it's a moment in time snapshot of their source tree.
Okay.
Does that address your question?
Yeah, I thought you were talking more about int values for a UUID.
Cool. Okay.
So you say you package up all dependencies. How far down do you go? Are we talking like libpython 2.so or like even libc6?
Excellent question. I lived in fear of this question. So everything I've told you is a lie. Here's what actually happens, is we define a few fixed points, and we then build against those. So we define a version of glibc, a version of GCC that it was compiled with, and a version of Python, and then that's defined as a platform. And that platform might move forward, but probably won't. It is pinned at a moment in time ABI-wise, and everything references back to which platform it wants to run on. So we don't actually package up the Python interpreter, right? We can just say we want Python 3.5, we want Python 2.7, we want Python 0.1, whatever. And that is, in a sense, a symlink. What we do package up is the bits that we ourselves move. So both the things that Facebook has written, all the Python that Facebook has written, all the C++ that Facebook has written, and all the Python and C++ that third parties have written that we use. That's what is contained within the PAR. Everything else is contained within the platform.
Okay, I think one more, and there was one. Here we go.
So has the onset of something like Docker changed your perspective on packaging Pythons and the dependencies?
So containerization is used pretty extensively within Facebook. But in a sense, it's made this work more important. Because when you're rapidly spinning up and spinning down containers, and when you have a whole bunch of containers that are running alongside each other, the ability to have a self-contained thing to run becomes very, very important. So all of our infrastructure for stand-up, sit-down, fight on containers is actually built around the concept of distributing a relatively small set of files and then running those files. And so this has become integral to all of that working.
Okay, everyone, please thank Dan for his excellent talk. Thank you.
Thank you.